Today I am going to talk about Newton's divided difference method. So here is the problem statement. During a catalytic oxidation of ethylene in a batch reactor, reaction rates are measured at different temperature 340 Kelvin, 345 Kelvin, 350 Kelvin and 355 Kelvin. To optimize temperature control, we need to determine the precious reaction rate at 348 Kelvin. So reaction rate data are given. So temperature versus rate reaction data are given here. So we have to find out what will be the reaction rate at temperature 348 Kelvin. For that, here I'll use Newton's divided difference method. So first we have to know what is Newton divided difference method. So Newton divided difference formula is Fx is equal to f of x0 plus f of x0 to x1 then x minus x0 plus f of x0, x1 and x2, where x minus x0, x minus x1 plus so on. So where divided difference are f of xi to xj is nothing but f of xj minus f of xi, xj minus xi, and f of that xi, xj and xk, that is f of xj xk minus f of xi xj and xk minus xi. So now, from given data, so you have to make the table, divided difference table. So here is the divided difference table. So already the formula is given, and f of xi xj is nothing but f of xj minus f of xi xj minus xi. So here temperature data are given 340, 345, 350, 355, and our reaction rate is given 0.0428, 0.0512, 0.0607, 0.0715. Now first divide difference, so that is here. So fxj means that 0.0512 minus f of xi divided by that xj minus xi. So if we do the calculation, we will get 0.00168. Similarly, again that third one minus second one of reaction rate, and similarly divided by that third one minus the second one. So 0.0607 minus 0.0512 divided by 350 minus 345, that will give 0.0019. Similarly, that here, so again the last one reaction rate minus that previous one 0.0715 minus 0.0607 divided by 355 minus 350, so that is 0.00216. Similar way we do the second divide difference using first divide difference, divided difference. So for here, so we got that second one 0.0019 minus 0.00168 by 350. Now here you have to check that x value. Now 350 minus 340, so that will give 0.002. Similarly we will get that second term of second divided difference, so that is 0.00216 minus 0.0019 divided by 355 here minus 345, so that will give 0.00402. Now finally third divide difference we have to calculate. So using second divide difference, so second one minus first one divided by 355 minus 345. Remember the range of the x denominator. So here the third divide difference is 0. Now using the data, so here I have to calculate here that T is equal to 348 Kelvin. So we will use 348. So here, so it is close to 350 and 345. You can, so for that we have to take x0 here. X0 is 345 and x1 is 350 and x2 is 355. Okay, so now here actually we have to calculate that reaction rate at T is equal to 345, so that it is near to 350. Okay, so we are taking that x0 is 345, x1 is 350 and x2 is 355. So now using this data and fx0 is 0.012. So here fx0, so we are taking this value, so 0.0512. okay, I am taking this value and then 0.019 and 0.0002. so here fx0 is that 0.0512, fx0x1 is 0.0019, fx0x1x2 is 0.002. Now here is our that Newton divided difference formula, and we have to plug that. So here I am plugging, so 0.0512, then here 0.001 into x minus x0. X minus x0 is here, so 348 minus 345 plus again this value that f of x0 x1 x2, so 0.402, then x minus x0 x minus x1. So here that is 0.002, 348 minus 345, then 348 minus 350. Now first term is 0.0512, second term will be 0.0057, and third term, if I do the calculation, will get minus 0.0012. Now if I add all together, so finally rate of reaction at 348 Kelvin, so that will be 0.05678 mole per liter second. So now if you verify the result, so result should be, so here 0.05678, 0.0658, so result will be lies between that 345 and 350, so that will be between 0.0512 and 0.0607 mole per liter seconds. So now our result is in between, so we can verify the result. So now we learn that Newton divided difference method. That's it. Thank you.